All right, we are in time here, so let's start. So first of all, the next exam we will be doing in November, right? November 10th. Yeah. So I will tell you which chapter we will cover there next week. That's about the exam, and let's continue with this chapter 5. So in thermodynamics, there are few terms that we need to define. So one is a system, S-Y-S-T-E-M. So what is a system in thermodynamics? Something that I want to study is called system. So if I want to study about one thing, that is called a system. Yeah. So let's say I have a thing here. So maybe this is a stone. This is a stone. I want to study about this stone here. How much heat it absorbs, how much heat it loses, what will be the temperature if I put it in the oven or something like that, right? So thermodynamics is all about the temperature and heat, right? So anything that I want to study is called system. So this is the system. So this is the rock or whatever I want to study. So what will be the temperature of this one if I heat for a while? What will be the temperature of this rock if I put in ice or something like that? So that is called system. Anything that we want to study is called system. Yeah. So let's say I have a beaker here. So this is the cup. So you already know in the laboratory. So I have some water here. So I have some water here, and I put it in oven. So this is a heater here. Heater. So now, if you just want to study about this water, so water is your system. Makes sense? But if you want to study about this water and this beaker together, then that water and the beaker makes a system. Yeah. Maybe some water is being evaporated here like this. So if you want to study this vapor, this water, and the beaker together, then those three things makes a system. So system is basically you define yourself. Oh, what do I want to study? I just want to study what happens in that water. So what is the system? Now I want to study about the water and the vapor going out here. So the vapor and the water becomes the system. Now if I want to study this vapor, this water, and this beaker together, then that is my system. So system is basically I define myself. Make sense? Everybody got that? So what is a system? So you define your system, what you want to study, and that's called your system. Yeah. So this is a system. So let's say sometime this is the pipe, right? So this is the pipe. In this pipe, the hot water is flowing like this. So hot water flows in the pipe like that. So this is the pipe here. So if somebody wants to study only about this water, so that becomes the water, right? So the water company guy comes to our home and look about the water and study about that water, what is wrong, what is right, and that flowing water becomes his system. Make sense? So maybe this pipe has some problem. So this pipe may have some problem. So this pipe, the water guy cannot study that pipe, right? So we need to call the engineer from another company to look the pipe, right? So he comes there and look about that pipe, and he is studying about this only pipe without this water. Then that pipe becomes his system. Make sense? Or maybe somebody is expert enough to study the same time the water and this pipe together, so he defines both as a one thing, and that becomes a system. Yeah. So whatever we want to study, that is called the system. Yeah. Good. Alrighty. So that's a system. So, I just define a system as, let's say I want to study about this water here, and this water is my system. So I imagine a line between this water and this cup there, and that is called the boundary. Yeah. So I just imagine there is a line that is separating my beaker and air with the like this. So it is a imaginary line. So you just imagine a line that is separating the system with the surrounding here. Surrounding. So surrounding is outside part. Something that is not system is called surrounding. So this is outside is surrounding. So between the surrounding and the system, you put a very thin imaginary line, and that is called a boundary. So this is a system, and everything outside here is surrounding, and I just make a thin imaginary line here between this system and surrounding. So outside, so system is what I want to study. Outside everything, outside of system, everything is surrounding, and I imagine a very thin line that separates the system with the surrounding is called the boundary, right? The boundary. Make sense? So just like that. So let's say if you want to study about the laptop, heating and cooling system of laptop like this, so your laptop is a system. So the laptop is a system, right? And then outside the laptop, whatever you have is a surrounding. And you imagine a thin boundary line around this laptop, and that is called the boundary. Make sense? But if you want to just study what happens inside, there is a battery here in the laptop. But if you just want to study about that battery, so just I want to study that battery. So the battery becomes your system, and outside everything is surrounding, and draw a small line, the imaginary line between the battery and the surrounding, and that becomes the boundary. Make sense? So basically what you want to study or analyze in detail, that is the system. Yeah? So, like that. So I will put something like this. So the boundary, so if there is a beaker with water, so let's say like the exam question, so like this one. So I have water here, and then I put this picture and define the system. If you just want to study about the water, so you are going to draw a line here. That's so just the water, right? Make sense? So define a system if you want to study the water and outgoing vapor. So this is the vapor. So you may want to draw the line like this one, right? So including the water and the vapor, right? So define a system if you want to study the beaker containing water plus the water and the vapor, everything. Now this becomes your system. Something like this. You just draw the line, yeah? Good? All right. So here. So there are something here I put the picture. So let's look about this. So we have 3 kind of system. So one is open system. So we have 3 kind of system. One is open system. So open system is something like this. So you have a coffee in this cup, and this is a hot coffee here, right? So open system. So does it lose mass or it doesn't lose mass? It loses mass. Why? Because it's hot, and so water molecules are evaporating and it's going out like that. So if you remember that carbon dioxide experiment, we are mixing hydrochloric acid with some carbonate and we'll use the carbon dioxide out, right? So we are losing the mass, yeah? So if we are losing the mass, we are also losing the energy. Since mass is not different from the energy. So because energy, so if you remember from yesterday, the kinetic energy is equals to half mv square. So if you are losing mass, you are immediately losing the energy because that energy has this. If there is a mass, there must be energy. Make sense? If we are losing mass, meaning that we are also losing the energy. There is no difference between mass and energy. Mass is energy, energy is mass. Make sense? So this is losing the mass here. So in open system, we have something here, and it is losing some mass, and also it is losing energy. So if something loses mass, means that it immediately lose energy. Yeah, you really don't have to understand if something mass is being lost, is it energy is being lost or not? Yeah, definitely. If mass is being lost, mass is the energy. Yeah. So open system is something that lose mass as well as the energy. So example is a coffee cup without cover. Yeah. So if I cover tightly here, the water will not go out, right? So the open cup with the coffee here is a open system. So it is losing the mass and it is also losing the energy. So if it is really cold here, so maybe heat may be coming out from here, or water may be coming from outside and condensing and going in. So maybe something may be coming in. If coming in or coming out, yeah, the same thing. So it's an open system. The mass can go out or mass can come in. The energy can go out or energy can come in. So this kind of system is called open system. Make sense? So now closed system. See, closed system. So closed system is like this. So you have a bottle. So water bottle here. So this is water bottle you buy from the market. So there is water here. There is water here. So this lid is tight here. So this is very tight lid there. So water molecules are not going out, right? So if you buy one bottle of water and put here, so measure one today. So that's maybe 1 kilogram. Come tomorrow and again measure 1 kilogram. Another day 1 kilogram. Put here 1,000 day and come after 1,000 day and measure again. It's still a 1 kilogram, right? So mass is not being lost. Make sense? So mass doesn't go out. So mass from here, the mass doesn't go out, mass doesn't come in. Yeah. So the mass here is always constant. So closed system is mass is not changing. Not changing, meaning mass is not lost or gained. Lost. So there is no hole here. So the water molecule or anything from here cannot go out. Mass is not lost or can come. So mass also can come in. Mass can come in. So if this is 1 kilogram, always 1 kilogram, right? Make sense? Now, if this is the hot water, let's say this is the hot water. So you boil in home, so put water in a bottle and you tightly cap here and bring the water to campus. So after 1 hour, all hot is gone. So it becomes cold, right? So it lost the heat energy from the wall to the surrounding. Make sense? So it becomes cold. So water is not lost, but energy is lost. So energy is lost, or energy can come in. Make sense? The energy is lost means you put the hot water here, tightly cap here, water cannot go out, but this water becomes cold. Why? Because the heat goes out from the wall like this. The heat, it loses the heat from the wall. Make sense? So something like this is called closed system. So closed system does not lose the mass. It only just either become cold or it becomes hot. Yeah. If you put it in hot, it becomes hot. If you put in cold, it becomes cold. Right? Why it becomes cold? Because it loses the hot heat energy from the wall outside. Yeah. Good. So like that. Now energy is lost. In closed system, mass is not lost, but energy is lost. Or you can say another way. So I'm just using the lost there. So maybe you can use the term gain also. So this is the, let's say, copper bottle here, copper bottle, you have water here. So tightly capped here, you put in heater here. So I'm just heating it. The water is not going out, right? Water is not being lost, right? It's a closed system, but the water is being hot here. So it is absorbing, then it becomes hot. So maybe it is going in, but the mass is not coming in or going out. Yeah. Good. So this is a closed system. So let's talk about the isolated system. So we need to cap very tightly, and there should not be any hole in a closed system. Now let's talk about the isolated system. Isolated system. Isolated system. So there is no isolated system in the world. So the close to the isolated system is the thermoflask. So we have a thermoflask. So this is a thermoflask, right? So this is thermoflask. You put a hot food or hot water here. So they put a lot of things here to make it thick one. So they put a lot of things here and make really thick one, and they put a cork here. So cork means it is made up of wood, like that. Yeah. So this is really thick here. So thermoflask. This is thermoflask. So what is thermoflask? So you buy a bottle and put water, and it can put hot water, and it can keep the water hot for a long time, maybe 1 day or maybe 2 days, right? But there is no thermoflask that can keep the hot water for many days, right? So there is no isolated system. So isolated system is something you put mass water here. So in isolated system, mass is not lost. Mass is not lost. So tightly closed here. So any water molecule cannot go out, or water molecule also cannot come in. Mass cannot come in. Mass is not lost or there. Okay. Mass is lost, not there. So both ways, since it is tightly closed, right? So how about the energy? So energy. So if you put hot water here, maybe it is hot for 5 to 10 hours or maybe 2 days, right? So it really keeps the material warm for long time. So it is. So we say that it does not lost. So heat is not lost. Heat is not lost. So it does not lose heat out because the wall of these thermoflasks are really thick, so they don't allow the heat to go out. Yeah. So energy is not lost, mass is not lost. Make sense? In open system, mass is lost, energy is lost. In closed system, mass is not lost, but energy is lost. But in isolated system, mass is also not lost, energy is not lost. Right? So there is no ideal isolated system. So the close to the isolated system is thermoflask, but there is not really not very good isolated system. So this system may work for 1 day or 2 days. After 2 days, the water is going to be cold, right? So if we can make an isolated system that works for 1 month, we will make tons of money, right? So we warm the water, put in the thermoflask, and if it can make the water, keep the water hot for 1 month, that will really people are looking those kind of device, right? So, but we cannot make something like that. Have you got that? So, like that. So it is asking, this is the book problem. So it is saying, suppose we are studying a reaction occurring in a beaker on a table. It's just like you put the sodium carbonate and put hydrochloric acid, right? Like the lab number 7. So lab number 8. On the table laboratory, what constitutes the surrounding? So it is saying, so let's say you have this beaker, and you are putting some sodium carbonate, sodium bicarbonate here, and you are putting some HCl here, up, down here, and you are seeing the carbon dioxide coming and going out like this. So what is what constitutes the surrounding? So I will say this thing I will study just these things here. So HCl and carbon dioxide, HCl and carbonate, and it is CO3. Maybe I define those two things in my system, and this beaker plus whatever outside is there, I define them as a surrounding. Make sense? Good. So we will study that in, I think, lab number 10 or something like that. So we will measure the heat, how much heat is lost, how much heat is lost if we react sodium carbonate with hydrochloric acid. Yeah, but in lab number 8 we were doing how much carbon dioxide is lost. But in thermodynamics we will do how much heat is lost. Yeah, so like that. So the surrounding. So I defined my those chemical reacting material as system, and beaker and outside everything is the surrounding. So now energy transfer. There are some terms we need to know. So let's say you have a cylinder here, or you can put a beaker as well. So let's say this is the beaker, and it has water, and you put it in a heater. So this is heater. So it's heater, right? So you put the water in heater. Does the heat go from water to heater or heater to water? So heater is too hot, right? It's a high temperature. So this is hot. It's very hot, and this water is cold. So heat always go from hot body to cold body, right? So heat goes from heater to water like this. So water becomes heat because the water absorbs the heat from the heater, right? And it becomes hot and it boils, right? So heat, if your system is taking the heat, so this is your system. So this is your system that is taking the heat. So in this case, that heat we measure as plus. So heat, if this system, this is your system, it is absorbing the heat. So we take that heat as plus, Q plus, or you can write that. So that heat we give it as Q plus. Yeah. So if you see something like this, plus 30 joule. So plus 30 joule. So the change in heat is plus 30 joule. So this is your system, and this is saying plus 30, meaning that this system is taking 30 from here to here. Yeah. So that plus sign is regarding to the system, is not the other thing, not the heater. So we are concerned only with this water here. So if I'm saying that there is a plus 30 is going on, plus 30 joule is going on, meaning that this system is taking plus 30 joule from heater to water. Make sense? Because water is my system. I'm not studying heater, right? I'm studying the water. Make sense? So let's say so that's a plus. So now let's say you have a water here. So you have water here. So it's a hot water. So this is hot water. This is hot water. And you put this beaker in ice. This is ice here. Ice. So the heat goes from here or here? Here to here or here to here? Definitely heat goes from hot to cold, right? Like that. And then the water becomes cold later, right? So this is my system. I'm not studying ice here. I'm studying this one. So my system is losing the heat, right? So in that case, I write, okay, the heat lost by my system is minus. So I write the minus like this. Make sense? So first of all, I need to know my system. So my system here is water. So my water is losing the heat. So just like this is me, I'm expending my money, meaning that I'm losing my money, right? It's just like the money thing. Yeah. So if I say, all right, so I lose 30 joule, the heat change in my system is 30 joule. I write like this, minus 30 joule. It means my system lost 30 joule of heat energy to the ice and it becomes cold. Make sense? Alright, so like that. So here, if you put this guy in the heater, the heat will flow this way, and this gas becomes hot, and that is the heat is absorbed by the system, and that will give the plus. So if you put this guy in the ice and it loses the heat to the ice there, and it becomes cold, and it is losing heat, so we write that is a minus. Yeah, good. Thermodynamics is a lot of this kind of plus, minus, and this kind of term, so we get lost easily. So let's do another here. So thermal equilibrium. So what is thermal equilibrium? Let's say thermal equilibrium. Thermal means heat. A kind of temp, rather than heat is a temperature. So let's say this is one body. Let's say it's an iron piece, right? Iron piece. So iron block or whatever. So this is, let's say, another iron block. So we have two iron block here. You can put a thermometer here. So you can put a thermometer here. You can put a thermometer here. So this is already hot. Let's say it is at 80 degrees centigrade. So the temperature of this iron block is 80 degrees centigrade. Somebody already put in oven and heat it, right? 80 degrees centigrade. And let's say this is 25 degrees centigrade. So this is showing 25 degrees centigrade here. See that? Now this is iron. This is also iron. It can be other thing also. You can put a copper, you can put water or ice, you can put anything, yeah? But they have different temperature here. Now you can connect these two things with a small wire. Yeah, small wire. Now what happens if I connect this with a small wire? This is hot, 80 degrees centigrade. This is cold at 25 degrees centigrade. So the heat will flow through this wire. So the heat will flow this wire and go from here to here. So until both the block have the same temperature. Make sense? So at the beginning, when I start with the experiment, it was 80 degree, it was 25 degree. Now I connect these two with the wire, and this comes to about, let's say, 50 degree centigrade, and this goes up about 50 degrees centigrade. Now both of these things have the same temperature. Make sense? So this condition is called thermal equilibrium. So I have $100. Somebody has just $20, right? So I give my money to him. So let's say I have $100 here, and somebody has, so maybe let's say this is a person has $100, another guy has just $20. So this guy is going to give him money. So how much money he can give so that both of them have equal amount of money? Make sense? So 60. So if this guy gives $40 to him, $40, so he will have $60. Now, since he gives $40 there, now this guy also have $60, right? So something like this. Make sense? Everybody got that? So both will have the same amount, same heat there, and if the temperature of this both is same, we call they are in thermal equilibrium state. Yeah. So let's say I have 50 degrees centigrade here. Another I have also in 50 degrees centigrade. I connect this with a wire. Does heat go from here to here or here to here? No, it doesn't happen. Since they both are saturated, they have equal temperature. So if temperature is equal, the heat does not flow from one to another, right? So if you have $100, I have $100. It is not necessary I give you any money, or it is not necessary I get money from it, because we are both equal. We have both equal number, right? So that's like that. So thermodynamics is most of the time it's like the money thing. So thermal equilibrium means when the two things are equal temperature, and if I put them together, the heat does not go from one to another. Yeah, so that's called the thermal equilibrium. So heat transfer occurs spontaneously from the object at high temperature to the low temperature. But transfer of heat continues until both objects are at the same temperature. When the temperature becomes same, the heat transfer stops, right? So this is called the thermal equilibrium. So now exothermic and endothermic process. So what is exothermic process and what is endothermic process? So you already did experiment, and when you were mixing the zinc and iodine and you were setting, and when you touch it, it was hot, right? So when you are doing the experiment and you feel that there is a warmth produced, that is called exothermic reaction. So exothermic means exo. So it gives out heat. Exothermic reaction. Exothermic means it gives out heat. It gives out heat. It gives out heat. And your reaction vessel becomes warm. So reaction vessel or reaction mixture becomes reaction mixture. MIXTURE mixture becomes warm. So if you remember from the lab 6, when you put zinc with the iodine and you just set it, and when you are just tossing it, it was warm, right? So zinc iodide reaction is an exothermic reaction. Make sense? So if you remember from lab 7, but in lab 7 we are really using a very dilute solution. If you take NaOH and react with HCl, it also gives out heat. So you take the some HCl here and dump NaOH there, and you toss the wall of that aluminum glass. It also feels warm. Yeah, make sense? So those kind of things are called exothermic reaction, meaning that we do the reaction and it gives out the heat. And if I toss that glass where I'm doing the reaction, that's that feels warm. So if you take another reaction here, so you are putting some carbonate here, and you are dumping some hydrochloric acid in this one, and when you touch it there, it also is warm. So when does hydrochloric acid react with the sodium carbonate, sodium bicarbonate in lab number 8, so you feel warm there too. So it gives out the heat. Make sense? So when you are doing the reaction or doing something and your system is giving out the heat, so it's becoming warm, so that means exothermic. Yeah. So heat is all from the process, just like that. So when we do the reaction, heat comes out and the system becomes warm. So put sodium hydroxide in water, it gives a large amount of water. So if you take a beaker here and you have some water here, dump some piece of sodium hydroxide here and touch it, it becomes very it's not warm, it really becomes hot. Yeah. So dissolving process. As the sodium hydroxide dissolves in water, it gives heat, a lot of heat out. So that's exothermic process. Yeah. And the solution becomes if we want the fuel, so for example, propane. So propane, so this is fuel. In fuel, we have this carbon hydrogen bond here. So if we want this fuel, so this bond break and give large amount of heat out, so that we can drive the car or we can warm our house. Yeah. So burning with the fuel also gives a lot of heat, right? Make sense? So when we burn the fuel, it gives a lot of heat. So with that heat, we warm our house, apartment, drive car. So now this is exothermic process. Now how about endothermic process? That's the opposite. It absorbs the heat. So if the reaction vessel becomes warm, our reaction gives out the heat, and that is called exothermic reaction. Now endothermic. So is there a plus or minus sign? Maybe I write in the next slide. I will show you later. So endothermic. So what is endothermic? So you are doing the reaction. Let's say you are doing the reaction. So you have something here. You put water here, and you put the thermometer here, and let's say at the beginning it is showing 25 degrees centigrade, right? 25 degrees centigrade. Now put ammonium chloride there. So NS4Cl, dump NS4Cl, ammonium chloride in this water here, and look what happens to this thermometer. So the temperature goes down and become maybe 18 degrees centigrade. It's cool, become cold, right? So this is called endothermic process. Make sense? So there was more heat here. So as I put the ammonium chloride here, the water gives out some heat when it mixes with this one and it becomes cold. Yeah. So that's called endothermic reaction. So endothermic reaction does not give out heat but absorbs heat and becomes cold. Yeah. So another example is this is ice here. So this is ice. So if this is ice cube, if I need to melt this ice, it absorbs the heat. So it absorbs heat from outside and it becomes melt and become water, right? So ice always absorb water, absorb heat and it melts. Yeah. So if your system is absorbing absorbing heat, then that is called the endothermic. So endothermic process. Yeah. Good. Endothermic is something it absorbs heat and melts. Ice absorbs heat and melts, right? So that's also endothermic process because ice absorbs the heat. So if it is given out, that is exothermic, and if it is absorbed, that is called endothermic. So unit of energy. So you look at your electric bill and they write something there. So unit of electric bill or energy is a joule, joule or kilojoule or megajoule. So joule. So basically like the gram, right? So unit of mass is gram and kilogram and upper unit, something like that, right? But for energy, it is joule and calorie. So we have the unit of energy is joule and calorie. So this is not that often used in our food, but calorie is most of the time it is used in the bottle. So if you have a Coca-Cola here, so they write 100. So this is the Coca-Cola. So you read, you look here in the label, they write 140 calories. So they dump a lot of sugar there, and that sugar gives energy, right? 140 calories. And but if you are drinking the diet Coke, so they don't put sugar there. So they put something like other kind of the material that is sweet in taste, but it's not a sugar. It does not digest. So they write 0 calorie here, 0 calorie diet Coke. So meaning that you drink it, it feels like the Coke, but it really does not give the energy because there is nothing to give the energy. Yeah, make sense? So 140 calorie here energy. Okay, so the energy unit are either joule or calorie. So there is a relationship between the joule and calorie, just like milliliter. And so how do you convert the milliliter to liter? So you use this factor. So 1000 milliliter is equals to 1 liter. So with this factor, you can easily convert liter to milliliter, right? So similar factor exists between joule and calorie. So 1 calorie is equals to 4.18 joule. 4.184 joule. Yeah. So 1 calorie equals to 4.184 joule. So let's convert this one. So I bought so most of the time I told you in food in United States, I never see any packet writing the energy content in joule. They always write in calories. So go to the market and buy food and look the how much calorie is in the Coke, how much calorie is in the milk or any food, right? So they never give in joule. They always give in calories. So we need to do the conversion. So let's say we have one liter Coke here. So let's say it says I have 300 calorie in this Coke. So how many joule it has? Now we can convert that this calorie into joule by using this factor. So I have 300 calories. So I want to convert this calorie to joule. So I put that factor in such a way that I cancel this calorie and I got joule there. So I put 4184 joule up there and 1 calorie down here and calorie cancel. So 300. So it's about 1200 joule of. So I multiply this and this one. So 300 calorie. If the bottle is 300 calorie, there is 1200 joule of energy. Yeah. Make sense? So in our food packet in the United States, we never see the joule in the packet. We only see the calorie, and we can convert calorie to joule by using those factors. You got that? Just the conversion. So here is a problem. Convert 3.75 to the power 3 calorie into joule. So 3.75. So 3.75 into the power 3 calories. So 3, this is calorie. So we need to convert that into joule. So what I do is I put this factor to cancel the calorie. So I put the calorie down here, 1 calorie, this factor down, and 4.184 joule here. So calorie cancel. So you multiply with this one, and you get whatever the number is the joule. Make sense? Sure. Something practical, right? So you can go to the supermarket today and you say, oh, what's the calorie here? Yeah. So I never paid the calorie content previously. So I was getting some trouble with my body, and I started to count the calorie. How much calorie I am eating today, or something like that. Yeah. So when you become old and your body starts give you trouble, then you start to pay attention to the calorie. Otherwise, we just buy and eat everything. So now specific heat capacity. So specific heat capacity. So what we do is specific heat capacity is what you should do is like this. So you take either 1 gram or 1 kilogram of anything, not other. Either you take 1 gram or 1 kilogram of anything. So I take water here, that is 1 kg, so 1 kilogram. So I take 1 kilogram of water here. Make sense? So how much mass? So to define the specific heat capacity of anything, we need to take 1 kilogram or 1 gram of that thing. Yeah. So I take 1 kilogram of water here, and I put a thermometer here. And you already know that the temperature of this water in our laboratory is approximately maybe 22 or something like that, 22 degrees centigrade. Make sense? 22 degrees centigrade. Now I put this in oven. And I start to heat it. And this thermometer temperature start to go up. So it becomes, I heat until 22 becomes now 23. So 1 degree centigrade. I need to increase the temperature just by 1 degree centigrade. Yeah. If it is in 22, I need to go up to 23. If it is in 17, I need to go up to 18. Make sense? So we need to take 1 kg of water, and then we need to put that in the oven, and we need to put thermometer there. And if the thermometer says 22, it's heating here, and from 22, my temperature goes to 1 degree up, right? So how much heat energy it absorbs, if this water absorbs from here to here, to change the temperature from 22 to 23, that amount of heat is called specific heat capacity. Make sense? So specific heat capacity is amount of heat needed to change temperature of 1 kg of something by 1 degree centigrade, 22 to 23. If there is 17 to 18. And how much water I should put it here? 1 kg. Make sense? So what is so I say, let's say water has a 4200. So specific heat capacity of water. Water is 4200 joule per kg per degree centigrade. So per degree centigrade, meaning that if I take 1 kg of water and I want to increase the temperature of the water by 1 degree centigrade, I need to supply 4200 joule of heat energy there. Make sense? Like that. Good. Sometimes they write the 4100, sometimes they write 4200. It's the same thing. So 4.4100 joules per kg degree centigrade. Or I don't need 1 kg there. I can put 1 gram. So I just put 1 gram here, just 1 gram, and I put the thermometer. So it is in 22 degrees centigrade, and I heat it to up to 23 degrees centigrade. And for 1 gram, it takes if I take 1 gram, it takes about 4.1 joule. 4.1 joule per gram per degree centigrade per water. 4.1, right? Make sense? So if you take 1 gram water and you are heating it from, let's say it was 22 degrees centigrade, and after certain time it becomes 23 degrees centigrade. So how much heat it absorbs? The water absorbs. So 4.1 joule. Make sense? So this is in terms of the gram per degree centigrade. This is in joule per kg degree kg. The bigger. So 1 kg takes a lot of heat, right? Make sense? So specific capacity is I need to take 1 gram of something and I need to heat it so that the temperature changes by 1 degree centigrade. And how much heat it absorbs to do that? That amount of heat is called specific heat capacity. Specific means for 1 gram or for 1 kg. Have you got that? Like that. So heat capacity, amount of heat required to increase the capacity of given material. The first one, the amount of heat required to raise the temperature of 1 gram of substance by 1 Kelvin. So 1 Kelvin or 1 degree centigrade is same here, yeah. So don't get confused with the Kelvin. So if it says a Kelvin or it says the degree centigrade, it's the same thing, yeah. So heat capacity. So the former one is the specific capacity because I am taking 1 gram. So next one is a heat capacity. I just take a specific term from there. So specific heat capacity means you can take any amount of material. So I take 5 kg water here, 5 kg water here, and I put it in oven, and I change the temperature of this water by 1 degree centigrade, and how much heat it absorbs, that amount of heat is called the heat capacity of that. If I take 1 gram or 1 kilogram and I do the experiment, that becomes the specific heat capacity. Yeah. But if I take any amount of water, any amount of the material, and I heat it, and how much heat it absorbs, that is called the heat capacity. Yeah. Make sense? So I think we are in time, so we'll discuss it next. Yeah. Thank you very much, everyone.